Well, thank you, Dan, for presenting this material. There's a lot of opportunities here. The URAs, the undergraduate URAs, are a really good way. Part-time URAs are really a good way to get started for the summer URAs. Just remember that. So if you're interested in an area, try and start there. Now, I'm teaching a 489 like a lot of other people. I've taught this 3 times. This is the third offering. It's on computational sound. Now, I'm looking for people who 3B or later, so they've had the scientific computation, but they're really interested in sound, math, electronics, and students who want to do an independent project in one term and get course credit for it. And it's open to math, physics, engineering, everybody who wants to do this. All necessary material is going to be done in the class. Now, sorry. Okay, what's the grading? The grading is lectures with term work, 50%, project 50%, no final. Now, the term work is going to be experiments and homework exercises. I'm going to do the demos in class in MATLab, which is a MATLAB work-alike open source. But you can do the assignments in any language you want. And now the project, you can work alone or in groups. And you have an option to present the work. It's really open, the project. I'll say a few words in that in a moment. I put up a schedule. And the schedule is going to have, the main point of the schedule is we're going to have introduction to acoustics, and we're going to go through electronics and hardware in the beginning. And then we're going to have project stage points. We'll call them P0, P1, and P2, which is the final. So the project topic will be negotiated during the term. A 1-page proposal around week 6. 3 pages, that's wrong. 3 pages, I forget where that was, and end of term, the final project. Now a bit about the computing platforms. PC Linux, you can use a USB interface like this, and we've developed some software for measurement, which you may use. And you can work in Windows, and we also have National Instruments card, which is an oscilloscope, function generator, frequency analyzer, which runs under Windows. We've got 10 of these available for your use. And you can also work on Arduino, or you can work on Raspberry Pi. Now, so I'm just looking for people who want to do stuff. Now, so here are some past projects. Music synthesis, software modeling of an old school analog synth, automatic pitch detection, make a guitar tuner, analysis of bird calls, bioacoustics. So I've listed a number of topics there. Now, how are projects going to be graded? Well, I'm really, really flexible. I want to give grades based on contributions that whatever you can make. For example, you can collect your own data. You can analyze others' data. You can write new algorithms. You can evaluate others' code on multiple data sets. You can build hardware. You can contribute to open source projects. All that's fair game. How much work is required? I'm aiming for less than real-time compilers and graphics, but the choice is up to you. Okay, so now I just want to give just a real quick case study of why we should care about audio and why it's an interesting area for computer scientists. Well, I've got here a mixer, and this mixer now is controlled by your iPad. So if you go outside to any clubs, you'll see a guy walking around with an iPad, and he'll be fiddling with the levels of the guitar from the audience by this method. So this is connected by wireless to this thing. It's also connected by a MIDI cable to a tactile feedback device. Now, so what I can do is I can pull up this mixer. Now, I have to connect to it. Hold on. Okay, so I have to connect to it. So what I do is I connect to it, and then now I connect. Okay, so this is really interesting because here now I have a mixer, and I have a microphone, and I have an amplifier. So test, test, test. So there you can see the level on the left-hand side of channel 1. And here's the output. Now, this mixer can do all kinds of stuff. Like one of the things we can do is we can do real-time spectrum analysis. So if we go to utility, okay, so here's the real-time analyzer. Now, this is showing test. This is showing the frequency analysis of this thing in real time. So there you can see that. So this is a real-time spectral analysis display, and the amazing thing happening is that this thing is taking the signal in, and in 1.8 milliseconds it's producing an output. And we can verify that it's doing this. And so there's all kinds of signal processing. So this is real-time signal processing, where I may do something like I can apply an equalization, for example, to this. And now if I look at this, well, it's hard to see, but I've taken a notch out of the thing. But all this is happening in real time. So we're going to be doing analyzing how to do these algorithms. So this is the sort of the core part of the course, but you can apply these methods to all sorts of areas of your choosing. Okay, so are there any questions? Okay, so I'm happy to talk to anyone. As I said, I'm looking for people who want to come in and do their own projects. You've been here 3-4 years by the time, and I want you to do something you really want to do. Okay, so this is what it's about. Thank you.